Four 8-bit characters.
All right, let's get started. If you have not done so already, a reminder that your mini project pitch report is due by tonight midnight. If you have not looked at it at all, I highly recommend you go look at the details of what's needed on the mini project page. It lays down exactly what's expected from the report. The reports that were submitted by, I think, 5 p.m. last night have already been graded. So some algorithms are already chosen. So if you are starting off now, it would be a good idea to go and look at those and make sure you're not picking something that's already picked. Any questions on this? Again, a reminder, the quiz will be on Monday. We'll start at 1 p.m. sharp. We're done at 1:10. We'll have a 5 minutes break, and then the lecture will start at 1:15. So on Monday, we started to look at directed graphs, and in particular, directed acyclic graphs. And a directed acyclic graph, as the name suggests, is a directed graph that has no directed cycles in it. And these are very natural graphs that come up when you have a bunch of jobs that you want to do, and they have precedence relations. That is, you have an edge from job I to job J, then job I has to finish before you can start job J. And if you draw this directed graph and it has no directed cycle, this means that all the jobs or the precedence relations are consistent. So topological sorting or topological ordering of a DAG is an ordering of all the n vertices in a graph, so that if you draw the first guy on the left and then go from left to right, and then you draw all the edges, then they have to move forward. So they all have to go from left to right. If that is the case, then the ordering is a topological ordering. Last time we had argued that if a directed graph has a topological ordering, then it necessarily has to be a DAG. And the intuition is simple. If you have a directed cycle in your graph, there is no way you can order things so that they are consistent, right? No matter how you order them, there will be one edge that will go back. Then we started working on the other direction, where we wanted to argue that if your graph is a DAG, then there indeed does exist a topological ordering, and that the way we're going to prove it is by presenting an algorithm that, given DAG as an input, computes a topological ordering. And so here's the algorithm that we maybe went by a bit quickly at the end, so let me go over it again. So again, the graph is given as input a DAG. If the graph has just one vertex, and that means it has no edges in it, then the topological ordering is simple. You just output that singleton vertex, let's call it U. If not, there's a lemma that we stated that we'll prove today, which says if the graph is a DAG, then it necessarily has to have a vertex W so that it has no incoming edges. Okay, so this is something that we have not proved, we'll prove today. But if there always exists such a vertex, and if there's more than one, then you can pick any. So let W be one such vertex. And then you look at the graph where you throw away the vertex W and all of its incidence edges. Okay, and we didn't prove this last time. I gave it as an exercise, which if you haven't done, you should, is to argue that if you start off with a DAG and throw away one of the vertices, what's left is another DAG. And the intuition is, by throwing away vertices or throwing away edges, you cannot create a cycle when there were none to begin with. And then what you do in the topological ordering is output W first, and then recursively call the algorithm on the new DAG G prime. So let's see how this runs on this example that we had before. So if you look at this graph, which is a vertex with 0 incoming edges? What's your name?
Sam.
Sam?
Sleeping.
Sleeping, right? So there's no incoming edges. So by the algorithm that we have, we're going to put sleeping in first, then we remove sleeping and all of its outgoing edges, right? And now the interesting thing to note is that there are two vertices in this new graph that have 0 incoming edges. It's taking a shower or taking the bus. Oh no, sorry, I take it back. That is not the case. Shower is the only vertex that has 0 incoming edge. There is an incoming edge to bus from here. All right, so then you put shower next. Again, you throw away shower and all of its outgoing edges. Then the next one is taking the bus, so you put it in next, throw it away. The next guy is the other class, you put it in, throw it away. Then lunch is the only one with 0 incoming edges, so you put it in, throw it away. And now you're in the base case, the graph has just one vertex. So in this case, you should just output whatever's left, which is 331. And this is exactly the topological ordering that we had looked at earlier. Any questions on this? The problem statement, the algorithm? So in particular, I said if you draw all the edges, then they are all going forward as they should. Questions? All right, so remember there's that line in the algorithm which says pick a vertex W that has 0 incoming edges. We have to argue that there exists one. And this was lemma 3 from last time. And then what we are going to do is a quick runtime analysis of topological ordering. We are not going to explicitly argue the proof of correctness. It just follows from induction. But we are not going to do it explicitly in class. All right. Any questions before I start? All right, so we had stated this lemma that I think we were calling lemma 3 last time, which says if G is a DAG, then that necessarily implies there exists, and let's say this is graph on vertex at V, then there exists a vertex W such that W has 0 incoming edges. Okay. And surprise, we're going to use contradiction. So we're going to prove it by contradiction. Everyone okay so far? Okay, if so, then what should we assume for the sake of contradiction if we want to prove lemma 3 by contradiction? Alex?
There does not exist a with no incoming edges in the DAG.
Right. So again, remember when you have an implication, the negation is you assume the antecedent is true and whatever is being implied is false. Right? So assume G is a DAG, but all vertices have at least one incoming edge. So again, this is the logical negation of the implication that we want to prove. And so here's the idea. Since this is true for all possible vertices, pick any one arbitrary vertex, W1. We know it has an incoming edge, right? So let's say its incoming edge is coming from W2. Similarly, W2 will have another incoming edge. Let's say it's W3, and you can keep on doing this argument over and over and over again because we know every vertex has at least one incoming edge, right? So let's say we run it to Wn, and then let's do it one more time. Okay. So we kind of repeated this process so that we have essentially picked n edges, and we have n plus 1 vertex labels, right? So we started off with a vertex being labeled W1, then W2, then W3, and kept on going till we ended up with a label Wn plus 1. And again, the reason you can do that, and you can of course keep on doing it forever if you wanted to, but the reason you can do that is because every vertex has an incoming edge. Okay? So what we have is there are n plus 1 labels, but we know by definition there are n nodes, right? Because that's what I've started with. But there are n nodes. So now we apply the pigeonhole principle, where the pigeons are the labels and the holes are the nodes. And so since there are more labels than nodes, it has to be the case that two labels refer to exactly the same node. Okay? So this implies by the pigeonhole principle. Actually, someone pointed out it's same as PHP, not the kind that we would usually use, but so by the pigeonhole principle, there exists I not equal to j, and in fact, let's assume that I comes before j, such that wi is equal to wj. Okay? So all this is saying is if you have more labels than nodes, they have to repeat, and let's say the two repeats are wi and wj, and wi comes before wj. So what's happening over here? I have my wi, and then maybe I have my wi plus 1, and I keep on doing it till I get to wj minus 1, and then I know that the incoming vertex that we have chosen wj is actually identically equal to wi. Right? And so what do we have over here? We have a directed cycle. Okay? So that implies a cycle which contradicts G being a DAG. Okay? And so that's it. So talk to your friends for half a minute. Let me know if you have any questions on this whole topological ordering business, the algorithm, which we still have to analyze its runtime, or any of the lemmas that we have proven so far. All right. Are there any questions? Tyler.
You say there's n plus 1 labels and nodes. What? I don't know how to n plus 1 labels.
So what I'm saying is, label is, I'm just saying I start off with W1, it has one incoming edge, look at the guy that's pointing to it, W2, do the same thing again. But I'm never guaranteeing that the thing that are going to next is unique, right? They could repeat. So that's what I mean by label, right? So these W1 to Wn plus 1 will have exactly one of the n values of the n nodes. And so that's the point. You're choosing n plus 1 values from a set that's of size n. So there should be two pickings that will have the same number or vertex. Any other questions? All good? Okay. So we're going to go back to our algorithm for topological sorting or complete topological ordering. Again, I'm just going to write down what was already there. If V is the vertex set is unique, is a singleton, then return the ordering U. Let W be a vertex with 0 incoming edges. Then define G prime to be the graph that you get by throwing away vertex W. And then you return the ordering W followed by the topological ordering of G prime. Okay. So I said I'll leave the proof of correctness as an exercise. All the lemmas that we have proven is sufficient to prove correctness along with induction. Okay. So what we're going to do is analyze the runtime of this algorithm. And as we have done a couple of times, we're going to go in two steps or more than one step. So first we're going to argue that you can do it in O of n squared. And then later on, we're going to show that you can actually do it in linear time. So again, remember, graph on n nodes and m vertices, you can represent in theta m plus n elements. So this is indeed a linear time, or it can be implemented as a linear time algorithm. All right. So we're going to look at this O of n squared, and for the time being, assume that you can actually compute this new graph G prime in order n times. This is slightly shaky. You can make it more precise, but let's just assume this is the case. Okay. And so let's look at the algorithm. Well, the first step is simple. It's just doing a simple check and then returning something. So this is constant time. The next thing that's, we have to figure out is figuring out this vertex W, right? And so if we have to figure out a vertex W that has 0 incoming edges, the first step, maybe we should figure out, if I tell you a candidate W, can you quickly figure out what that vertex, whether that vertex has in degree 0 or not, right? So the more specific question is, given a vertex W in V, how quickly can you figure out if W has 0 incoming edges? And as a reminder, we are assuming this is the adjacency list format. So what does this mean? This means for every vertex W, you have two lists. You have the list of all incoming vertices. And you have the list of all outgoing vertices. So for each vertex, you have both of these lists. And so given this and given a vertex W, how quickly can you figure out whether W has 0 incoming edges or not? Alex,
O one,
O of 1, that's correct. Why?
because all we have to do is see if there's anything in that out, or the incoming list.
Right. So if W has no incoming edges, then all you need to check is whether this list of incoming guys is empty or not. So you want to check whether this is empty or not, and checking whether, say, a linked list has anything or not is a constant time operation, right? So checking is empty is a constant time operation. So this implies O of 1 time. All right. So if I can tell, given a specific vertex W, whether it has 0 incoming edges not in constant time, how much time would you need to do the computation for step 2? I have to ask your name. Adam.
O1.
Now you need more than O of 1 in worst case. I have to ask your name, I forgot, sir.
Brandon.
Brandon.
O9.
O of n, right? So the most, once you know, given a vertex W, whether it has 0 incoming edges or not, you just cycle through all possible vertices and check whether there exists one, right? So for step 2, go through all vertices W, right? So this is O of n. So now if you look at this algorithm and you kind of for the moment forget about the recursive calls, but in each recursive call you're spending O of 1 time here, O of n time in step 2. We have assumed that you spend O of n time in step 3, and whatever returning this is kind of constant of O of n time. So what we have over here is O of n time for each recursive call. But then the thing to note is whenever you make a recursive call, you're throwing away one vertex in each recursive call, right? So again, the recursive call where there are n vertices takes O of n time. Each recursive call, you're throwing away one guy. Right? So in the worst case, or in actually all cases here, you're going to run this. The number of recursive calls would be at most n because you're throwing away one vertex at each time, and each call takes O of n time. So what we have over here is we have at most n recursive calls since each, oh my. Because in step 3, you're throwing away the vertex W that you're choosing. So this implies overall runtime is n times O of n squared, which is O of n squared. Okay. And so that completes the argument for why this algorithm can run in O of n squared time, assuming we can do step 3 in O of n time. Okay. So talk to your friends for half a minute. Let me know if you have any questions. If not, we'll move on to trying to prove the better bound of order amplitude. All right. Do any of you have any questions? Grant.
On that last one, which says n times O and n squared.
Sorry. Should be off n. Any other questions? Otherwise, what I written was absolutely incorrect. Maybe I should just start making errors on purpose just to see if you guys are awake or not. Any questions? Is everyone okay with the algorithm and with the O(n) squared runtime analysis? Okay. All right, so we're going to do order m plus n, and it's not hard, but you have to pay close attention to the algorithm to bring the runtime to order m plus n. Okay? And in general, this will be a case where you might write an algorithm to do something, but then you have to really sit down and think hard what actually is needed by the algorithm. In particular, we'll see that in step 3, even though it says create this new graph G prime, you don't really need that information. Right? You don't need to completely compute G prime. Why? Because when you call the algorithm on G prime, all you need from that is to be able to figure out line 2. Right? And if you think about it for a bit, the only property that you need from G prime is not the entire graph, but what is the correct in degree of every vertex in that graph. So the important observation is, if we know the in degrees of every vertex at any recursive call in the algorithm, you're good. You don't need any other information. Right? And that is the observation we're going to exploit to go down from n squared to m plus n. If you actually insist on really recomputing G prime every point of time, you're not going to get it. Okay? All right. All right, I give up. So we want to go to order m plus n, and it turns out to help our analysis, it will be good to introduce a few more notations. So recall that for every vertex, you have the number of incoming guys and number of outgoing guys, and we'll just denote the size of these as in of w and out of w. So remember, previously we were using n of w to denote the degree, and there was no directions. But now we want to separately keep track of number of incoming neighbors and number of outgoing neighbors. So in of w and out of w are number of incoming and outgoing neighbors of w respectively. One result which follows from a similar result that we had proved for undirected graphs, but I'm not going to do here, so it's an exercise, is if you sum up all the in degrees of a vertex, that's same as the sum of all out degrees of a vertex, and both of these quantities are exactly n. Previously we had degrees that there was essentially the degree was in plus out, so that's why you got 2m previously for undirected, but for directed you get exactly m. I'm going to make use of this identity fairly often. All right, so the next result we are going to argue is that each recursive call takes order in degree plus out degree plus 1 time. Again, this W is the W that's picked in step 2 of the algorithm. So whenever the algorithms run and you pick the vertex W in the second step, that's what this W refers to. By the way, I don't know how many of you paid attention or noticed, I have this +1. Any guesses why I have this +1 in here? I forgot your name, sorry. Jared. To be more precise, if you have a vertex that has no incoming or outgoing edges, right? If you didn't have this +1, then you would say you would do that in order 0 time, which is 0 time, and that's obviously not going to happen because you at least have to throw that vertex away, right? So this +1 is a way to handle the corner case where a vertex is completely isolated, there's no incoming or outgoing edges. So this is to handle All right, so I'm saying for each recursive call with vertex W, I take order in degree plus out degree plus 1. So that implies overall, the time is, you sum over all possible vertices of order in degrees plus out degrees plus 1. And by the properties of big O, you can push the sum inside. So sum of in degrees plus sum of out degrees plus n, because you're summing 1 n times. And this we have just seen is both of these are m. So that would be order m plus n. So assuming we can prove lemma 4, we have argued that the runtime is order m plus n, but we still have to do that. And as I said, to prove lemma 4, we'll really have to use the observation that we do not need to compute all of G, but we just need to keep track of the in degrees. And in particular, we don't even need to keep track of in degrees explicitly. All we need to figure out really quickly at each point of time is one vertex with 0 in degrees. Right? But it turns out to do that recursively for all calls, you should also keep track of the in degrees. So that's one way to do it. So we're going to argue this, and I said the main observation is only need to keep track of in degrees and do not need to compute all of G prime explicitly. Okay. So what I'm going to do is I'm going to tell you the two data structures we're going to keep track of, or we're going to create. And then just going to quickly walk through and argue that the initialization takes order m plus n steps for both of these data structures, as well as the total update time, and the update time is basically this order in degree plus out degree plus 1 business. All right, so the data structures that we're going to maintain is we're going to maintain one array that keep tracks of in degree of each vertex, and then we separately keep track of all vertices that have in degree exactly equal to 0. So in degree is array of length n, such that if you look at in degree of W during any recursive call of the algorithm, is the in degree of that vertex in that particular graph. Okay, so by the way, sorry, in of W is also called in degree, out of W is also called out degree. So number of incoming edges and number of outgoing edges. Okay. And when I say current G, I mean the graph G in the current recursive call of the algorithm. And then you have separate linked lists of all vertices W with the in degree being 0. Thank you. So are the two data structures clear? Okay. So we now have to figure out how much time it takes to initialize. So we initialize the in degree of each vertex to the actual in degree that you start off with. How much time would it take if I give you a specific vertex W and I ask you to compute its in degree, given that, again, recall the graph is in the adjacency list representation for directed graphs. How much time would it take for a given vertex W to compute its in degree? I can wait. Jordan? Sorry? Jared, sorry. It can be more than O of 1. Okay, so it's O of 1 assuming someone has already computed size for you. But, and this is an important thing to remember, when you're theoretically trying to analyze all of these runtimes of lists and stuff, there are lots of pre-built functions that exist in, say, Python or whatever that you cannot assume is true unless you use that initialization time too, right? So in this case, what you really need to know is figure out the size of the incoming list. And so in worst case, if its size is enough W, you have to kind of walk through all of them, right? So, and you also have to, again, handle the annoying case where the in degree is 0. So this is order of in degree plus 1. And so of course this is only for one vertex W. So overall the time to initialize the entire matrix is sum over W of order in degree plus 1. Again, I can take the sum inside. And so then you get order m plus 1. Okay. So basically what you do here is essentially going over each and every entry in the adjacency list, and you potentially are spending an additional order n time going through each vertex. All right. To initialize L, once you have this in degree, how much time would it take for you to initialize this linked list L, which remember is all vertices with in degree 0? Assuming you have completely computed this in degree array. Alex? Yes, why?
Because it's possible that every vertex has
No, so what's your algorithm to get O of n?
You're asking,
If I give you n of w, how would you compute the linked list cell?
I would step through in degree W and
Right. So again, as I've been trying to tell you over and over again, my questions are generally not trick questions. So it's don't get scared. So the idea is once you have this in degree, all you want to figure out are all vertices W, so that indig of W is 0. So how do you do it? Just scan through the list. So scan through in degree and add W to L if in degree of W is actually equal to 0. And so you're just doing a scan and constant amounts of work each time. So this is over n. Okay, so that implies overall initialization is order m plus n, which is good because we want to order m plus n at the end, right? So your initialization better also be order m plus n. Okay. All right. Any questions so far? All right, so once we've initialized these two data structures, in each recursive call, we basically need to figure out this vertex W. So we need to figure out how we query, and it turns out in this case more important how we update the data structure. So query is we want one vertex that has in degree 0, and that's not trivial if we have this linked list cell. Any of those guys are okay, because they're all of in degree 0. So let's say we delete the front of L to get W, and so this is order 1 for vertex W. And remember, we want to argue that each of these recursive calls, you can do it in order in degree plus out degree plus 1. So being able to do something in constant time is definitely A-okay. Okay. All right, so the more interesting part is update. And so this is the part that will replace step 3. Instead of computing G prime completely, we're just going to update these two data structures. Okay. And so what are we doing? We have this vertex W that has only outgoing edges. And so the idea, of course, is we're going to throw away this vertex W. If I throw away this vertex W, which locations in the in degree vertex should I go and make changes? So let me write it down. If we delete W, what are the vertices U such that in degree of U needs to be updated? If I'm only throwing away W and its outgoing edges. Sorry, Mark.
Every node in LW.
Right, so every vertex that's an outgoing neighbor of W are the only vertices whose in degree is going to change, nothing else is going to change. So what we are going to do is, so here's how we do it. For all outgoing edges, all we need to do is we need to decrement the in degree of all the outgoing. Right? So if there is any vertex u that has w as an incoming neighbor, you decrease this in degree. And while we are doing this, we can also see if a value suddenly becomes 0. And if that's the case, we'll just dump it into L. So if in degree of u is equal to 0, add u to L. And so the point to note is all of this is constant time. Right? And the number of times you're going to run this loop is out degree of w by definition. Right? That's the number of outgoing neighbors. Okay? So overall update is order out of w plus 1. Sorry, so update time is this, so that implies overall update or query is you sum over all vertices of order out degree plus 1, and again you have that plus 1 because, for example, you have it plus 1 over here, but you could also have plus 1 over here just in case, for example, there are no outgoing edges. And so this will be order m plus n, which you can't see. And that's it. So talk to your friends for half a minute, a minute. Let me know if you have any questions. Otherwise, we are done. Are there any questions? All right, you might not want to leave because there's an important piece of information that you might want to know about. So whatever I said till before this, everything is on the midterm. So in terms of the book, all of chapters 1 to 3, with the exception of section 1.2, everything, whether we covered it in class or not, if we didn't cover it in class, it was a reading assignment, and hence is on the midterm. Okay. And as I said, there's a Piazza post with more details on the structure of the exams and all the other fun stuff. So that's all I had. If you did not pick up solutions to homework 3, I have some copies up front. Don't forget, yeah, Mark.
Are we still going to have homework the week of the midterm?
As a last question, do we have an exam the week of midterm? No, but there's one which is going to be due the week before. Okay. So there's going to be one out this Friday and due next Friday.